This is Lab 5, the spinning ball in projectile motion. What is this lab about? In this lab, I will be analyzing and predicting the motion of a ball's projectile motion and its change in internal energy by using the energy principle, Newton's second law, and Python. We will be able to see if the internal energy does change and how it plays roles in everyday objects if it does. To do this, my computer model will update the ball's position based on different forces acting on the ball and assuming frictional/air resistance forces are negligible. I will then calculate the internal energy by finding the other energies in the system and then using the energy principle. For my results, I got that the change in internal energy was about 5.3 times 10 to the negative 3 joules, which shows there was a difference in internal energy, though it was small. The main physics principles needed in order to analyze the ball's motion include Newton's second law, which states that the final velocity is equal to the initial velocity plus the net force over the mass times the change in time. This will help to predict the motion of the ball in the Python model by seeing what forces are acting on the ball. We will also need to make use of the energy principle, which states that the change in total energy is equal to the work done by the surroundings. Choosing the ball as our system, the work done by the surroundings would be equal to the work done by Earth, which is also equal to the mass of the ball times the force of gravity times the height of the center of mass of the ball. We also know that the total change in energy is equal to the change in internal energy plus the change in translational kinetic energy, which means that all of that is equal to the work done by the Earth. Now let's use these in a computational model. I found the initial velocity vector and the x and y components from the first 2 points given in tracker and then put it into the code. I then found the net force on the ball, which is just the force of gravity in this case, neglecting air resistance. I then used this force to update the velocity, and with this updated velocity I could then update the position of the ball. I also had to initialize my energies, stating that the initial kinetic energy is equal to 1/2 times the ball's mass times the magnitude of the velocity vector squared. And the potential energy due to gravity is equal to the ball's mass times the gravity force times the position of the ball in the y direction. In order to find the changes in energies, I updated the energies using the values I just found and then finding the difference between the final and initial energies. Now let's see what this looks like when I run it. As you can see in the upper graph, the total change in energy represented by the green line looks to be about 0, meaning the change in internal energy of the ball must be extremely close to 0, if not 0. You can also see how the gravitational potential, the red line, and the kinetic energy change, blue line, are somewhat cancel each other out to get the value of the opposite of whatever the internal energy is. In the bottom graph, you can see that in both the x and y positions, my model did fit the tracker observations of the position quite well. There are a few inconsistencies which can be due to not accounting for air resistance in the model or human errors in tracker. For example, on the graph of the y positions near the end of the model, the data starts to overpredict where the ball is going, possibly due to not accounting for the air resistance in the ball. Next, I had VPython calculate the change in internal energy for us. The change in internal energy was calculated by finding the change in translational kinetic energy by using the initial input velocity of the ball and the velocity of the ball at the end of its path. I found the work done by the Earth by finding the ball's mass times the force due to gravity times the ball's position in the y direction, or its height. I then did the gravitational potential energy minus the change in translational kinetic energy to get the change in internal energy, which Python printed out to be about 5.3 times 10 to the negative 3 joules. What does it mean? This positive change, what does it mean? This positive change in internal energy of the ball during the projectile motion came from the ball rotating during its flight and possibly an incredibly small amount of heat increase from air resistance. This goes to show that friction is not the only way many objects transfer their energy from kinetic, though it is a major one. An object's internal energy change must also be considered when predicting motion, though it is a small value and should therefore not hinder results by much.